Hi everyone, today I'm going to be doing the worked examples from exercise 6.5. So it's curve sketching from your jacplus Year 12 textbook. So in the book they give us this table showing us the different types of stationary point, and really, if we're looking at what the gradient would be or the tangent for each place, that is shown in this row here. So this is nothing new, but it's just handy to know the shapes and realise what that means for the gradient of those different graphs. So let's look at worked example 9, where we have to determine the stationary points and justify their nature. So I'm just going to cross out the justify their nature for a start, and we'll worry about determining them. So the big idea is that stationary points exist when the gradient is 0. So in this case, f dash of x equals 0. So if we're going to find when f dash of x equals 0, of course we're going to need to find f dash of x. So let's do that. So that will become 4 minus 4x minus 3x squared. And then now we just have to, equate it to 0. So neg 3x squared minus 4x plus 4 equals 0. And I'm going to divide everything by neg 1, just so we end up with a positive here, which is easier to work with. And of course, if we divide 0 by negative 1, it still remains as 0. So let's see, 3x times x and neg 2 times 2. And we get 6x minus 2x equals 4x. Yes, this works. So it means that in the brackets we'll go like this and like this. So we have 3x minus 2 and x plus 2 can equal 0. And of course that means x equals 2/3 and x equals negative 2. So what we know is that on this graph of f of x, the stationary points will exist when x is 2/3 or x is negative 2. Now they're asking us to determine the stationary points, not the stationary x values. And I mean, really, who's heard of stationary x values? It's a stationary point. So you would have to find the y value as a matter of course. So we're going to sub that into the y equation, of course, which is, well, the f of x equation. So let's do f of 2 equals 2 plus 4 times 2 minus 2 times 2 squared minus 2 cubed, and that is 2 plus 8 minus 2 times 4 is 8 minus 8. So 8 minus 8 is 0. 2 minus 8 is negative 6. So that means that our first stationary point when x is negative 2 is going to, now hold on, I've done that wrong here. Let's just go back. So we're subbing in negative 2, not positive 2. So let's do that again. So equals 2 minus 8, minus 2 times 2 minus 8, and then plus 8. So actually we end up with the same thing anyway. But yeah, that was just a fluke. So be careful to sub in the right thing. So our first stationary point is at negative 2, negative 6. The second one, when x equals 2/3, so let's go over here and do that. So f of 2/3 equals 2 plus 4. Minus 2 times 2/3 squared, and minus, minus 2/3 cubed. All right, so let's calculate that. A little bit annoying, it's got fractions in it, but nothing out of the ordinary. 8 over 3 minus 4 over 9 times 2 minus 8 over 27. All right, so let's see. So I'm going to make that 2 plus 8 over 3 minus 8 over 9 minus 8 over 27, and we'll make a common denominator of 27. So what's that, 54, plus 9, 8, 72, minus 3 times 8, 24, minus 8 over 27. So that is going to be 94 over 27. And that means our second stationary point's at 2/3, comma, 94 over 27. So this would be our stationary points for that equation, or that f of x. Now it's asking us to determine their nature. And look, there's two ways to do this, and I'll show you both ways. So stationary points at -2, -6, and what was the other one? 2/3, 94 over 27. So the first way to do it, and the way that the book no doubt shows, is that you will test a point on either side of the stationary point. So just say you have at -2, -6, so just say that's here. Then that could look like this. It could look like this, or it could look like this, or the other way. So it's either a minimum, maximum, or point of inflection. So the point of inflection could also go that way. The point is that if we find that the gradient at -3, for example, is negative, then we know that it can't be the purple graph or this one there. Then if we find that the gradient after -2, so just say -1, just say that's positive, well then it can't be this one because that's negative. So then you'd know it's a local minimum. So with that in mind, you can make a little table, and the table that you would make would look like this. You'd have an x value, you would have the gradient, and you would have what it looks like, or the slope of the tangent, you could call it if you really like. Now, the places we know are -2. We want to find out what's on either side of -2, and 2/3. So we want a value that's below -2, so let's do -3. A value that's above -2, we can put -1, but 0 would be nicer, easier to sub in. And notice that that's got to be before this, so it's going to be lower than 2/3 and higher than -2. And then something that's after 2/3, so higher than 2/3. So 1 would be the, the option to do. Now, our gradient function is, I have to go back and have a look, sorry. Gradient function, 4 minus 4x minus 3x squared. So let's go back. Where is it? Here. Okay. So f dash of x equals 4 minus 4x minus 3x squared. So now we can find the gradient at each of those points. So f dash of -3, 4 minus 4 -3 minus 3 -3 squared. So what's that? And for -11. So that means that the tangent slopes like this. We already know at -2 it's a stationary point, so the gradient is 0. And at 2/3 as well, so I may as well put that one in. Then at 0, if we sub 0 into f dash of x, you can see you're going to end up with 4. So that's positive up the hill. And then at 1, 4 minus 4 times 1, 4 minus 0, minus 3 times 4 squared, 16. Oh, sorry, not 16. We're subbing in a 1, not a 4. What am I doing? So, so 1 squared is 1. And that's a negative gradient, so it can look like this. So in other words, the shape would be like this. And you can see, therefore, -2, -6 is a local minimum. And 2/3, 94 and 27 is a local maximum. So if you go back to that table from the start that we looked at, we can see the shape looks like this for a maximum and the shape looks like this for a minimum. So this is one way to do it, and look, this is the way that you learn in the methods textbook. There is a more efficient way, which I will also show you, which definitely comes in handy for things like this. And this is where we use the double derivative. So I'll call this method 2. Probably should have called the other method, method 1. So method 2, find the double derivative. So in this case, we've got f of x. So the double derivative, or actually first the derivative function, is 4 minus 4x minus 3x squared. So 4 minus 4x minus 3x squared. So the double derivative is where we derive that twice. So we're going to get negative 4 minus 6x. And then what we can do, we can find, well, at x is negative 2. So we're going to get negative 4 minus 6 times negative 2. So negative 4 plus 12 there is going to give us 8. So this is a positive number. So there's a positive double derivative. And if it's a positive double derivative, it means it's a local minimum. So therefore, at negative 2, so at negative 2, negative 6, it's a local minimum. And we saw that it's a local minimum here. But we just did it a lot more quickly, like that. And furthermore, we can do the double derivative at 2/3. So that is neg 6, where's our double derivative? Neg 4, sorry, minus 6 times 2/3. There we go. So I'm just using that equation. I had a bit of a brain blank there. So we get negative 4 minus 12 on 3. So we get equals neg 4 equals neg 8. And this is a negative value for the double derivative, so this means it's a local maximum. If you had found that the double derivative equals 0, that doesn't help you. You're going to have to go and do this thing with the little table and find out what happens on either side. It doesn't mean necessarily that it's a point of inflection, but it is a really, really handy method to find whether you've got a local maximum or a local minimum. Much easier than the table. So that is worked example 9. Let's move on. Right, so the curve y equals ax squared plus bx minus 24 has a stationary point here. Calculate the values of a and b. Okay, so this is what I'd do in a question like this. I'd say we have the y equation and information, and we have the gradient equation. Or I probably will call it information. And, well, the y information is, well, y equals ax squared plus bx minus 24. And there's a point. It's a stationary point, but it's still a point that exists on that graph. So the point is neg 1, neg 25. In our gradient information, well, the gradient dy dx is 2ax plus b. And, well, the point that exists there is negative 1 for x, and the gradient is 0, because a stationary point means that the gradient is 0. So this I would call the secret point. And it's a secret point because they don't give us that point in the question. It just, you've got to know that the gradient is 0 at a stationary point. So look out for the secret point, because without it, you're not going to be able to calculate the values of a and b at all. So let's make two equations. Neg 25 equals a, neg 1 squared, plus b, neg 1 minus 24. So now we can say a minus b equals, we're adding 24 on both sides, so we get neg 1. So there's one equation, which I guess we can label if we want to. I might highlight it rather. Now, for the second equation, we've got 2a times neg 1 plus b equals 0. So neg 2a, sorry, plus b equals 0. So these are our two equations, which then we can really quite easily apply use simultaneous rules in order to solve. So I'm going to add these two equations actually. So a plus negative 2a is negative a, or negative 1a if you like. Negative b plus b, well, that's going to cancel the b's out. Neg 1 plus 0 is neg 1. So a equals 1, so we're dividing by negative 1 on both sides. That's one of our answers. And then for b, well, let's say 1 minus b equals neg 1. neg b equals neg 2, b equals 2. So that's our values for a and b. So in a question like this, if I were you, I would use the little table, at least until you get very confident with where the information has to go and where you've got a secret point, in terms of knowing that a stationary point exists on the y graph as the point, and it exists on the gradient graph as a point with zero gradient. So it means the x value stays the same, but the y value turns into the gradient value, and the gradient value of a stationary point is always 0. So I guess you could say the big idea of this exercise is that the gradient is 0 at a stationary point. Okay, so let's see. Did I do all of that? Yes. All right, so let's go for the next bit. So we have, I think this is the last one, we have to sketch this graph and locate x-intercepts, y-intercepts and turning or stationary points and justify their nature. State the domain over which it's strictly increasing. All right, so strictly increasing, I'm just going to write that straight away, f of b greater than f of a. So we'll come to that when we get there. Okay, so sketching the graph. Our checklist of things, which of course you don't have to write. It's y-intercept, x-intercept or intercepts. And now we're doing turning points, or stationary points I should call them. And shape. So they're the things we need to know. So it's probably easiest to do the y-intercept first. And you can see straight away it's at -8 because all those will cancel if you sub 0 into them. So it's at 0, -8. So we've got that, which is right there. X-intercepts. So half x cubed minus 3x squared plus 6x minus 8 equals 0. And, well, we're going to have to do a long division of polynomials, so it's really not very good. I'm just going to quickly cheat and find our p-value. I'm just going to look on my CAS. Or not our p-value, our p of whatever equals 0. Bear with me. All right, so it looks like p of 4 equals 0. So you can, you would obviously not start with 4. You would start with 1, -1, 2, -2, etc. But if I sub a 4 in, p of 4 equals 0, and therefore x minus 4 is a factor. So look, this is a bit of a long-winded question. It's a little bit annoying, and the chance of getting something like this non-CAS is very slim. Half x cubed minus 3x squared plus 6x minus 8. And look, you would do the long division of polynomials. Again, I'm just going to find that on CAS. Because it's quite a long thing to do just for that. So what we get is x squared minus 2x plus 4. So of course, if you were doing it by long division, you do this divided by x, the answer goes there, you multiply down, etc. So just normal long division of polynomials. So what that means is that now our y equals, so it's called y, equals x minus 4 and x squared minus 2x plus 4. So we can see that if we have x-intercepts, x minus 4 equals 0, so that would mean x equals 4. So actually we're equating to 0, aren't we? So x equals 4. And now this part here, we've got to see, well, can we factorize this to two linear factors? And I suspect the answer is no, actually. And how you can quickly find that is to say, well, what is the discriminant? So b squared minus 4ac discriminant equals neg2 squared minus 4 times 1 times 4. And yeah, as I suspected, 4 minus 16 is less than 0. So that means it's a negative discriminant and therefore no solutions. So what this tells us is that we just have one x-intercept when x equals 4. So we cut the graph at x equals 4, but that's it. So let's tick that. 4, 0 is our x-intercept. Okay, so look, let's now go for the stationary points, and then, the shape will come out within that. So stationary points exist when dy dx equals 0, and this is a y equation, so I'll call it dy dx. So our original is this, meaning that our dy dx is 3 times half is 3 over 2 x squared minus 6x plus 6. And let's equate that to 0. Okay, now we've got this 3 over 2 here, and if we divide everything by 3 over 2, I should just do it like that, divided by 3 over 2 on both sides, well, that's going to give us x squared minus 4x plus 4 equals 0. So now, well, we do x times x and neg 2 times neg 2. And of course, that's neg 2x minus 2x equals neg 4x. And look, you can probably see that this is the perfect square. So this is x minus 2, which is x minus 2 squared. So when that equals 0. So that's going to be x equals 2. So we got a stationary point at x equals 2. So when x equals 2, we need to find the point. So what y will equal? So y equals, is our equation? No. Y equals half x cubed minus 3 x squared plus 6 x minus 8. So, and now we've got 8 on 2 is 4, minus 3 times 4 is 12, plus 12 minus 8. So that gives us neg 4. So our stationary point at 2 neg 4. So let's pop that on. And now if we're determining the nature of that stationary point, so I'm going to go for the double derivative, and our derivative function is here. So our double derivative, d2y over dx, is going to equal 2 times 3 is 6, so 3x minus 6. And then, well, let's sub in when x equals 2. And that's, look, it's a little bit annoying because, well, that equals 0. So this is one of those ones where we have to say, well, what could it be? And we actually do have to do the little table in order to find that out. So we know that we have a stationary point when x is 2. So if I take something below that, 0 is convenient. And then I take something after that, well, I could take 3, but when I sub that into my dy dx, it's going to give me some sort of yucky fraction. So I'm going to choose 4 because then I'm going to get rid of the fraction. So we've got gradient and what it looks like, or what the tangent would look like there. So we know at 2 the gradient is 0, so that's the flat tangent, that's the turning point. So if we sub a 0, our gradient dy dx equals 3 on 2, what was it, 3 on 2 x squared minus 6x plus 6. So let's sub in 0. So that gives us 6. It doesn't matter if it's 6 or it's 26 or it's 106. What matters is that it's positive. You don't really need to write the 6 there, you could just write a plus. Dy dx when x is 4. So see what I mean by having a even value here? Well, it means that this 2 will cancel, so that's quite nice. 4 squared is 16. 16 times 3, 48, divided by 2 is what, 24? Minus 24 plus 6. So it means it equals 6 as well. So it's positive. This is a stationary point of inflection. So stationary point of inflection when at 2, and what do we find our y value to be? -4. Okay, so now it's just a matter of putting all that information together. I'll just do that. And we had the stationary point of inflection at 2, -4, so 2, -4. We had an x-intercept at, I believe it was 4, let's just double check. Yes, and a y-intercept at -8. And 4. So now we can just connect it up. This is a stationary point of inflection, so I hate putting it together. It's always difficult to get the shape. So something like this will be our graph, and that is showing all important features. So of course you should label the axes, etc. Now it does also ask us about the strictly increasing. I remember writing that there. So strictly increasing, what we see, strictly increasing means that your y value or your f of x value is going to be larger than f of a. So what that means, b is the value further along and a is the value more to the left. So as your f of b value is larger, so your y value is larger than if you sub in the value of a for all the x values possible. So it's for x is an element of R. So that would be our answer for part B. All right, there's one last one here, and I'm just going to do it a little bit quickly. So the video is not too long. So here is our rule. Specify the coordinates at the endpoints of the domain. Okay, endpoints. So 1 when x equals 1/4. Well, we can sub in 1/4, and I'm just going to cheat and have a look at what that is. So we sub in 1/4, y equals 1/4 over 2 plus 2 on 1/4, and that equals 65 on 8. So the first endpoint is 1/4, comma 65 on 8. And the second endpoint is at when we sub in a 4. So when x equals 4, y equals 4 on 2 plus 2 on 4, and that's going to equal 5 on 2. So the second endpoint is 4 comma 5 on 2. So there are endpoint, oops. Okay, so next, obtain the coordinates of any stationary point and determine its nature. Okay, again, stationary point exists when this is the function y, so we'll say dy dx equals 0. So let's do dy dx. So y is half x and plus 2x to the -1. So dy dx equals half minus 2x to the -2. So half minus 2 on x squared. So we have to make that equal 0. So half minus 2 over x squared equals 0. And now we can have -2 over x squared equals -half. And I'm going to divide everything by -1 so that they become positive. And then actually I'm going to make the numerators the same. So what I do to the top, I do the bottom. 2 over x squared equals 2 over 4. So this means I can cancel the numerators. I've got an equal sign there, meaning x squared equals 4 and x equals plus or minus 2. Now, we need to be careful because, well, not all values are necessarily within the domain. And in this case, we've got a domain from 1/4 to 4. So if the domain is 1/4 to 4, then reject x equals -2. So stationary point exists when x equals 2 only. So we've found the x value, it's a 2, and we need to state the nature of that stationary point. So I'm again going to go for the double derivative. So our derivative function was half minus 2 over x squared. And then the double derivative is going to be 4x to the -3. So now that I've got the double derivative, let's see if it's going to work. And you can see it's so much quicker to do it like this. So it's worth testing it out, you know, even if you end up with a 0 and have to recheck. So let's sub in the value of x, which is 2. So when x equals 2, d2y over dx equals 4 over 2 to the power of 3 is 8 equals half, and that's positive. So it's a minimum. Now recall that we have not found the corresponding value of y yet, so we will do that. Let's see, it takes a lot of working out here. X over 2 plus 2 over x. So when x equals 2, y equals x over 2 plus 2 over x, which is 2 over 2 plus 2 over 2, which is 2. So the stationary point, and we can say it's a local minimum, right, so local minimum at 2, 2. Now we're meant to sketch the graph and state the absolute maximum and minimum. So sketching the graph, we have our domain here. We have a local minimum at 2, 2. So that may be the absolute minimum or it may not. We've got endpoints at 1/4, comma, what did I get for that? 65 on 8. And we've got another endpoint at 4 and 5 on 2. And you can see that that's higher. 5 on 2 is higher than 2. So the graph will look something like that. And, well, we should label the axes. The absolute maximum is the y value where we are a maximum. So the absolute maximum is 65 on 8. And you can say when x equals 1/4 if you like, but really that's not necessary. The absolute maximum refers to the y value. So you should not put the point. That would not be correct. The absolute minimum refers to the y value that is the lowest on the graph, and that is 2, when x also equals 2. And that, I believe, is the end of the worked examples.